I would like to thank Mehmed and Daman for giving me the opportunity to talk here. So it's a pleasure. And as Daman said, I will talk about generalized Wronskian and give a few applications. So in the first part, I will recall or define what are generalized Wronskian and consider only a subfamily of them that we call geometric. And then as a second part, I will give a first application in hyperbolicity. So of course, I will give a short introduction in hyperbolicity to motivate the result. And then in the third part, I will talk about application in foliation theory. So I will give two applications. So as the talk is supposed to be divided in two parts, so I decided to in the first part, talk about the definition of Wronskian and the application in hyperbolicity. And in the second part, I will give a proof of this application and then the application in foliation theory. So I decided to do so because I think it's easier for people not familiar in the subject to understand the first part, whereas the second part, it might be a bit more complicated. So let us start. And let's start by setting a few notation. So for the talk, P will be a fixed integers. And we will consider words written with the alphabet 1, 2 until P. And we will consider two words to be the same if one passes from one word to the other by a suitable permutation of the letter. So say commutative word, and so we can write them uniquely in this fashion. And so we will not LU the length of the word, so the number of letters in the word. So to any such word, we will associate a partial differential operator defined as follows. So you differentiate alpha 1 times according to the first direction, alpha 2 times according to the second direction, and so forth. And so such differential operator acts on the sheaf of holomorphic functions in P variable. So once we set this notation, it's quick to define what are generalized Wronskians. And so the definition goes as follows. So we'll define pure generalized Wronskian, which is due to Wronski for P equal to 1 and Ostrowski for P strictly greater than 1. So we take U a set of words, so here of size, so we take M words, and we'll say that U is admissible if and only if the following condition holds. So we require that the length of UK is less or equal than K for every K between 1 and M. So of course, for this to make sense, one has to set an ordering in order to list the word of the set, the word in U. So we'll start by order the word of length 1 according to the lexicographic order, then of length 2 according to the lexicographic order, and so forth. And so then we can check this condition and say whether or not the set U is admissible. That being said, to any such admissible set, we can consider the following operator. So we take M plus 1 holomorphic function in P variable, and we form the following matrix. So on the first line, we put our function. Then on the second line, we put our function that we have differentiated according to the first word in the set, and so forth, until we exhausted the set. And so we obtain then a square matrix, and we take the determinant. So of course, by antilinearity of the determinant, here we can consider this sheaf, so where we take the tensor product, of course, over C. Then such an operator will be called a pure generalized Wronskians of size M. So when we have defined this pure generalized Wronskian, we can take the span of them. So define the vector space of generalized Wronskian, which is then the following. And so an element in this vector space will be called a generalized Wronskian of size M. So for example, if we take P equal to 1, then there is a unique admissible set of size M, which is the following. And so we recover the usual definition of Wronskian in one variable when we differentiate the function as many times as it takes to obtain a square matrix, then take the determinant. For p equal to 2 and m equal to 2, here I've listed all the admissible sets. And so we have 7 of them. And so in greater generality, it's a combinatoric thing to list all of them. So the fundamental property of generalized Wronskian is the following. So it is due to Bauchet for p equal to 1 and to Roth for p strictly greater to 1. And it says the following: if you take m plus 1 holomorphic function, then they are linearly independent over C if and only if one can find a generalized Wronskian, and we can always suppose that it is one of the canonical bases, such that when evaluated on the m plus 1 holomorphic function, it does not give for an holomorphic function that is identically 0. So this is really the fundamental property of Wronskians for p equal to 1 and generalized Wronskian for p strictly greater than 1. So for the talk, we will consider only subfamily of the generalized Wronskian that will allow actually geometric construction, so that we will do later on in the application. So the family is the following. So we consider simply the following subvector space. So we take the geometric generalized Wronskian, the generalized Wronskian that satisfies the following functional equation. So we require that if we multiply all the function by the same function, then it comes out, and the only possible power is m plus 1 here. And so an element in this space will be called geometric generalized Wronskian. So first natural question would be to ask amongst the elements of the canonical basis, the generalized Wronskian, to find which are actually geometric. It's not that complicated to find them. So we have the following definition proposition. So if we take a set of words, we will call it full if and only if the following condition holds. So if we take any word in the set, then we require that all its subwords remain in the set. So if this condition is satisfied, we say that the set is full. And the proposition is that if we take any full set of size m, then the pure generalized Wronskian associated to it is geometric. And we will call it accordingly a pure geometric generalized Wronskian. So for example, for p equal to 1, there is absolutely no difference between geometric Wronskian and Wronskian. Whereas for p equal to and m equal to, one can check that these ones are the only full sets amongst the admissible ones. So for instance, this set is not a full one because the subword 2 does not belong to the set. So a natural question would be, okay, so here we found amongst the canonical bases, the ones that are geometric, but can we find other? Actually, one can find some clever linear combination of pure generalized Wronskian that satisfy this functional equation. And so to find them, there is quite a natural way. So say that the group of B holomorphism of CP0 acts on the space of generalized Wronskian as follows. So we take B holomorphism of CP0, we take a geometric generalized Wronskian, and we simply act on it by reparametrizing the function via this B holomorphism. So by doing so, you imagine that you have your square matrix and the function differentiated. And so here you use the formula to compute partial derivatives of composition of function. So on which line you will have a certain formula involving the partial derivatives of the coordinate of psi, and you will develop then the determinant. And so you will find, so here I'll just give what one can find on an example. I think it's clearer. So for instance, here, if you take this Wronskian, so say the canonical Wronskian, where here we have privileged the first variable, and we let a B holomorphism act on it, then we find the following expression. So we have a polynomial in the partial derivative of the coordinate of the holomorphism here, and the coefficient of this polynomial are pure generalized Wronskians. And so here, what we find is that by letting the group of holomorphism acting on it, so we recover here the three, say, pure geometric generalized Wronskian, and we find two other ones here. So basically, in this example, it's easy to show that the vector space of geometric generalized Wronskian is of dimension 5, and here we have the basis. And so a natural conjecture is the following, is that if you take any p and any m, then the vector space spanned by the coefficient of this expression, so seen as the polynomial in the partial derivative of the coordinate of the holomorphism, it should be equal to the space of geometric generalized Wronskian. So in other words, this would give a really practical way to produce every possible geometric generalized Wronskian. So I've checked it in a few particular cases where, well, computation are still manageable, but it seems to be quite a complicated question in full generality, but quite easy to state, actually. Okay, so now we've introduced geometric generalized Wronskian, and for application, the really important property to have is that it should still allow to read linear independence of function, as the generalized Wronskian did. And so it turns out to be true. And we have the following. So if we take m+1 holomorphic function in p variable, then they are linearly independent over C, if and only if. So the weak form is to require that there exists a geometric generalized Wronskian which, evaluated on the function, does not give something identically 0. And the strong form is that actually we can do the check only on the pure geometric generalized Wronskian. So we require that there exists a full set on which it does not vanish identically. So depending on the context, sometimes the weak form is enough, but sometimes one needs the strong form. Okay, so this is it for the definition and properties of generalized and geometric generalized Wronskian. And now we will give a first application in hyperbolicity. So the goal of this part is to prove the following. So actually the result is quite easy to state, so we'll already state it. So if we take a non-degenerate Fermat hypersurface of degree delta in the projective space, so basically up to a rescaling, it's an hypersurface defined by this equation. You just take the homogeneous coordinate that you elevate to the power delta and you take the sum. And you see what are the points in the projective space that satisfy this equation. So consider that kind of hypersurface. And you consider an holomorphic map from CP to this Fermat hypersurface, and you require that it's non-degenerate, in the sense that if you take the differential of this map, and then you ask that there is at least one point when this differential is injective. Then the statement is that if the degree of the hypersurface is large enough, so strictly greater than n+1 than n-p, then the image of this map actually lies in another different Fermat hypersurface of same degree. So basically, an hypersurface that satisfies that kind of equation. So a few remarks. So the first one would be that, well, the existence of map from CP to a Fermat hypersurface is not complicated. I mean, it's not complicated to find some. So for instance, I'll give an example for p equal 2. So you take this Fermat hypersurface and you consider these maps. So you take WZ and you map it to this with the theta I being lambda square root of -1. So for p equal 2, and you can do the same construction for larger p. And in some sense, the result says I mean, if we reiterate it, that as soon as delta is large enough, this is the only kind of such map that we can find on Fermat hypersurfaces. So another remark is that for p equal to 1, the result is known, and it is due to green. And it's still specific to Fermat hypersurface. And for p equal n-1, so the dimension of the Fermat hypersurface, it's also known. And this actually is independent of the fact that it's a Fermat hypersurface. It holds for any hypersurface, because here the statement says that there are no holomorphic map from C to the power n-1 to the variety. And so it follows from a result of Kobayashi-Ochai. Okay, so this is the goal of this part is to give the idea of the proof of these results. So first, let me motivate it and give a short introduction in hyperbolicity. So we take X projective manifold, and by entire curve, we mean a non-constant holomorphic map from the complex plane to X. So basically, when we talk about hyperbolicity, at least in our setting, we will mean the study of the geometry of entire curves inside X. So for example, we can take the simplest projective manifold, so the one of dimension 1. So it's a smooth projective curve, said otherwise a Riemann surface. And in this case, there is a clear distinction regarding the geometry of entire curve, which is the following. So if you suppose that the genif of C is equal to 0 or 1, then C is covered by entire curve. For the genus equal to 0, we find P1, so it's obviously covered by entire curves, by line. And for G equal to 1, it's a quotient of C by Z lattice, so this is the same. Whereas for G strictly greater than 1, so greater or equal than 2, there does not exist any entire curve inside C. And to prove that, well, modulo, if one knows the Riemann uniformization theorem, it's very easy to show. So if you have a map from the complex plane to C, then you can lift it to the universal cover of C, which is the disk by the Riemann uniformization theorem. And so here you have the holomorphic map from C to C that is bounded because it lands in the disk. And so by Liouville's theorem, it must be a constant. So there cannot exist any entire curve in X. And so the main study of hyperbolicity, at least for projective manifold, is to try to understand the geometry of entire curve for projective manifold of higher dimension. And so what is expected, so for this behavior, is dictated by so the Green-Griffiths line conjecture that here we will state in a particular case. So here we take a smooth hypersurface of degree D, so which is the setting in which we stated the result in hyperbolicity, where we took a Fermat hypersurface. And the Green-Griffiths line conjecture in this case says the following. So if the degree of the hypersurface is large enough, so here the bound is polynomial in N, it is n+1, then it says that there should exist a proper closed algebraic subset that contains the image of every entire curve in X. So said otherwise, if the degree is large enough, there should not exist much entire curve, because if there are some, they should be included in something very specific. So in this case of hypersurfaces, the state of the art regarding this conjecture is the following. So first, it was proved by Diverio, Mercure, and Rousseau that for general hypersurfaces in Pn, the conjecture holds. So what do we mean of large enough degree? So what do we mean by general? It means that you fix a degree. So your hypersurface is given by a family of coefficients, giving the equation. And you say that you pick your coefficient in an open set. So say, otherwise, if you pick them randomly, roughly, then the result holds. And here, large enough degree, actually, the bound is very, very large. So it's exponentially n. So it's very far from this linear bound. This result has
your coefficient they are in Zariski open set, not yeah.
Yes, it's Zariski open set. Yes, exactly. Zariski of open set of the modular space of hypersurface of fixed degree.
Excuse me, Antoine. Just one question. Projective manifold, do you mean smooth projective variety?
Yes, exactly. And so this was for general hypersurfaces, and it was actually improved by Brodbeck. And Brodbeck proved the same result with also a very large degree. And he actually showed that in this case, we can take the proper closed subset Z to be empty. So just a bit of terminology in this case. So when there does not exist any entire curve, we say that the manifold is hyperbolic. So the statement of Brodbeck amounts to saying that a general hypersurface of IN of degree is hyperbolic. And in full generality, while we are quite far from the conjecture, as it is not even known that an entire curve cannot be Zariski dense. Because of course, if this conjecture is true, the first very simple corollary is that if you take any entire curve, its Zariski closure cannot be the whole space. And even in this, even this statement is not known. And so just for, to state the full Green-Griffiths long conjecture, it says that actually, this statement, so the fact that there exists a proper closed algebraic subset containing all entire curve, should hold for any projective manifold of general type. And here, of course, for an hypersurface, this amounts exactly to this condition. And just so people who are familiar with it, being of general types, by definition, is having the canonical bundle big. Okay, so let me give a rough idea of the strategy to attack this conjecture. So these ideas go back to Green-Griffiths, Hsu, and Demailly, and is roughly the following. So the first one is the construction of obstruction to the existence of entire curves. And here, these obstructions are algebraic ODEs, so in the case of entire curves, or PDEs, in the case of family of entire curves. And so this obstruction is that one finds a lot of ODEs or PDEs that must be satisfied by every entire curve on the manifold. So this is the first step, and so we will describe it more precisely right afterwards. But of course, to have the full conjecture, one has to understand really explicitly what are these obstructions. Because, okay, so we know that we have them, but we have to understand what geometrically they mean. And so, and this is actually the very hard part, which we cannot do yet. But in some particular cases, is that one want to really understand these obstructions. And if we believe in the conjecture, it should force the coordinate of the entire curve or family of entire curve in the projective space to satisfy algebraic equation. So being included in a proper algebraic subset. Okay, so now I will describe the first part of in detail, the first part of this strategy, because we do know it well. And so it goes as follows. So we take X, a complex manifold, still P a fixed integer, and we consider for K an integer, the fiber bundle of K jets of P germ into X. Okay, so we just explain the typical fiber of this fiber bundle, because it's actually a quite natural generalization of the tangent bundle. So the fiber of our point is simply the following. So you take all the holomorphic P germ, so that sends 0 to X. So of course here you pick trivializing chart for X, so that you can differentiate your holomorphic P germ according to, up to the order k. Okay, so you consider all the partial derivative up to the order k. Here, and this is the typical fiber of this fiber bundle of kjet of PGM. So of course, if in this case, as soon as k is strictly greater than 1, if we change chart for the manifold X, then it does not preserve the vector bundle structure of the fiber, and so it's only a fiber bundle. And so we have a natural action on it. So the group of B holomorphism of CP0 act fiberwise simply by reparameterizing our PGMs. So that being introduced, we can now introduce the, say, objects that will encode the algebraic ODEs or PDEs that we were talking about in the general strategy. And it is the following. So we fix D an integer, and we consider the vector bundle of PDEs of order k and degree D, so acting on PGMs. So once again, we will understand it fiber by fiber. And so a fiber above a point is simply the following. You consider the polynomial in the fiber of our fiber bundle of kjet of PGMs here, and we require that it is homogeneous of degree D with respect to the action of C star. So actually, this is not really important here, but just bear in mind that here we have really a polynomial in the partial derivatives and of the PGM, so we can really see it as a PDE, which is absolutely not linear, but still, this is the object that will be relevant in the study of entire curves. And so in this case, one checks that actually, when we change chart, the vector bundle structure is preserved, so it is indeed a vector bundle. And so, for example, for p equal to 1 and k equal to 1, here we only look at the germ of curves into X, and we look at their first derivative. So this is a way to define the holomorphic tangent bundle of a complex manifold. And so this is a generalization for higher order, for higher jets. And for still p equal to 1, k equal to 1, and any d, then actually this vector bundle is simply the symmetric power of the holomorphic cotangent bundle. So say we can see this object as a generalization of the symmetric powers of the cotangent bundle. Okay, so once we've defined this vector bundle, so we can state the result that justifies the first step of the strategy. And so this is the following. So you take X, a projective manifold, you take an ample bundle on it, and you consider a global section of the vector bundle we've just introduced, tensorize with the dual of L. And so the conclusion is that every holomorphic map from CP to X must satisfy the PDE defined by P. So what do we mean by that? If you take such an holomorphic map from CP to X, of course, you can see it locally around any point as a PGM. And so you can apply your global section to this PGM and see if it's 0 or not. And here, what we mean here is that it is always 0 for every point. So it really locally satisfies the PDE defined by P. So the global, so what says this theorem is that the global section of this vector bundle provides obstruction to the existence of such holomorphic map. But what's so this is actually the first part of the strategy. So as well, some people may not be familiar with so a few words here. So ample and bundle and global section. I just quickly recall that, say for the easy case, if you take an ample and bundle and you take two trivializing open sets, then the line bundle is obtained by at least on this the union of these two open sets as a gluing of these two copies of C by an aware vanishing holomorphic function. And if you have a covering of open set with a larger number of open sets, then it's still the case, and you require that there is a co-cycle condition so that it is well defined.
So your fiber bundle E here is a coherent sheaf. Do you know if it is a coherent sheaf or?
Yes, but since
okay,
yeah, it's correct, of course.
Okay.
Because, yeah, it's a locally free sheaf.
But it's
So
not,
yeah, of course,
it's not vector bundle, no?
Yeah, it's a vector bundle, so it's locally free sheaf.
Okay.
It is a vector bundle, yeah.
Okay.
So by global section, we mean of any holomorphic vector bundle, we mean a holomorphic map from X to E. So what does it mean? It means that to any point of X, we associate a vector in the fiber above X. And we require that this depends holomorphically in X. And so maybe for people that are more familiar with, say, differential geometry, require the fact that there exists global section for a given holomorphic vector bundle is something non-trivial. So we do not have partition of unity. So this is something, this is really a strong requirement. And here, the fact that we ask that it takes value in L-1 is even more stronger requirement. And finally, what we mean by ample land bundle, it's a land bundle whose powers have a lot of global section. And by nice, we mean that they allow to embed the projective manifold in a projective space. Okay, so this is for the first part of the strategy. And so here, so we mark on, well, to discuss it further. So there is really an equivalence between the existence of global section of this vector bundle for some KD, and the fact that X is of general types. So the first direction is due to component bound, and the other one is due to domain. So basically, it says that you have a good obstruction to the existence of entire curves if and only if you are of general type. So it's the first indication to the conjecture. But really, in its strong form, one should be able to really understand what are the geometric constraints of given by these global sections. So now to relate so these general ideas to study the geometry of entire curve on a projective manifold to what we discussed in the first part, so to generalized Wronskians. So we state the following proposition. So we take X a projective manifold, L an ample line bundle on it, and we take M+1 global section of L. We take a full set of size M, so it is associated to a pure geometric generalized Wronskian. And then one can show that the operator, so W index U, induces a global section, so that it will be denoted in this way, of this vector bundle. So observe here that we have a positive twist. And so locally, on a trivializing open set, it is simply defined as follows. So you take a PGM, so a holomorphic map from CP to X, defined around 0 that sends 0 to X, and you write your sections in a trivialization. So basically, what we mean by here is that, well, as we said here, locally, our line bundle is really U times C. So writing in trivialization here, we have really a map from U to C. So if we precompose this by the PGM, we find a map from CP to C. And so we can really use the differential operator associated to this this Wronskian. So we write our square matrix with the partial derivatives, and we take the determinant, and we define it in this fashion. And the fact that's, so this seems very local because it depends on the choice of trivialization here. And this is really where we see that the property of the defining property of geometric generalized Wronskian is important, because if we change trivialization, actually what one does is that one multiplies every one of these sections by the same transition function. And so by definition, it comes out. And so this is where this positive twist comes from. And this is what allows to define a global object via this local construction. But once again, we have here a positive twist. So it will turn out that in the case of Fermat hypersurface, one can manage to make this twist negative. And so we will I don't know if maybe I stop now, and then for the second part I will do the proof, and then carry on with the application in foliation theory.
Okay.